Very much. My dear learners, good evening and welcome to STEM Digital School, hosted by Africa Team Gigs. My name is Mr. Spiwe Sibanyoni, and I will be taking you guys for technical sciences today for grade 12 learners, and we are going to focus on Newton's laws of motion. You will remember that this is actually the first topic that you do in grade 12. We introduce you to Newton's laws of motion. But in grade 11 as well, you've been introduced to forces, and therefore when you began this chapter, you had an idea more or less about how forces work and so on. And now we are going to package them together and talk about Newton's laws of motion. Now, the outline for today's lesson is in our overview, we are going to look at the Newton's laws, and we'll have the features of the topic, and then we'll have an assignment where we'll be talking about how to apply the first law and the second law as well as the third law. And also we'll look into how you can prepare for the examination and basically what the examination is about. So in the overview, in our Newton's laws of motion, as per the examination guidelines, this is essentially what you need to know. Now, my dear learners, you will remember that for you to prepare for your examination, you need to use your examination guidelines. The reason for that is because your examination guidelines will guide you in terms of what you need to know in that particular chapter. Furthermore, it will give you the definitions as correctly as possible, because that is essentially how we are going to mark them in the examination. So remember, you need your examination guidelines so that you are able to get the correct definitions as you are going to see them in the marking guidelines at the end of the year, and also what you need to know with regards to this particular topic. Now today, we'll be focusing more on Newton's first law of motion as well as Newton's second law of motion. And in our next lesson, that is when we are going to look at Newton's third law of motion. Now, according to the examination guidelines, this is what you need to know. Number one, you must be able to state Newton's first law of motion. And there it is given to you. A body will remain in its state of rest or motion at constant velocity unless a non-zero net force acts on it. Now, it's amongst what you need to know, the laws, but we won't be looking into that for now. We are just simply outlining what you need to know, and we will dwell more as we engage on Newton's first law of motion. Secondly, you must be able to state Newton's second law of motion, and there it is stated for you. When a net force is applied to an object of mass m, it accelerates the object in the direction of the net force. Acceleration is directly proportional to the net force and inversely proportional to the mass of the object. Now, we will dwell more into it as well as we go through Newton's laws. Now, you are also required under Newton's second law of motion to use the equation Fnet is equal to ma to solve problems that involve forces as well as mass as well as acceleration. Furthermore, you must be able to apply Newton's laws to a variety of equilibrium and non-equilibrium problems, including, now when we talk about equilibrium and non-equilibrium problems, we'll engage further on that because this has to do with the net force that acts on an object. So these situations where we apply Newton's laws, we must be able to work with that for a single object. Now, it can be a single object that is moving on a horizontal plane with or without friction. Secondly, it can be for a single object that is moving on a vertical plane. Again, these Newton's laws, we must be able to apply them and apply them to objects that are made up of two bodies. In other words, that are made up of two objects. So we call them two body systems, and they are joined by a light inextensible string. And those objects, they can be on a flat horizontal surface. They can be on a flat surface that is definitely horizontal, and we can look at a couple of examples regarding flat horizontal surfaces. So that's essentially what we are going to look at. Now, what you also need to know again is that you must be able to state Newton's third law of motion, which is what we won't be talking about, but I'm quickly just highlighting it for you in terms of what you need to know for this topic. And there it states when object A exerts a force on object B, then object B simultaneously exerts a force on object A of equal magnitude but in the opposite direction. Now, furthermore, with regards to Newton's third law of motion, we must be able to identify and give examples of action reaction. Must be able to list the properties of action reaction pair of forces. Now, let us look now and dwell deeper into this particular topic. So we are first going to look at Newton's first law of motion. My dear learners, you must be able to state the law as it is on the examination guidelines, because that is how we are going to give you marks. I know you have textbooks, you have study guides and so on, and they might give a definition, and that definition you might find that it's missing some of the keywords, and that changes the meaning of that particular definition or this law in particular. As a result, we give you examination guidelines in order for you to be able to state the law as it is going to be marked during the year as well as at the end of the year. And this is how we state Newton's first law of motion. It says to us, a body will remain in its state of rest or motion at a constant velocity unless a non-zero net force acts on it. Now, what essentially does this particular definition mean? Now, this definition is basically informing us that when you have an object which we refer to as a body, and this object was already in its state of rest. In other words, this object is not moving. In other words, this object is stationary. Then that object will remain stationary. In other words, that object will not move. It will be at rest unless now there is a net force must be greater than zero. In other words, if I now come and I push the object, the net force is no longer zero. And if the net force is no longer zero, then that object is going to move. It will not remain in its state of rest anymore. The reason the object was in its state of rest, the reason the object was stationary from the onset, is because the net force that was acting on it was zero. But now this object is in its state of rest, and now you come and you apply a net force on it. In other words, you make the net force to be greater than zero. Then this object will no longer remain at rest. It will start to move. In particular, it will start to accelerate, because when an object has a net force, then that object will accelerate. And hence, when you look at this law, you can actually interpret it in two parts, where it actually means a body will remain in its state of rest unless a non-zero net force acts on it. It means if a non-zero net force acts on it, this object will not remain in its state of rest. That state of rest is only true if the net force is zero. In other words, when the net force is now greater than zero, meaning a force is being applied on this object that is giving you a net force of greater than zero, then this object will start to accelerate. Or that body will move at a constant velocity. Now, what are we talking about when you talk about a constant velocity? If an object is moving at a constant velocity, it means the velocity of the object is not changing. In other words, if an object moves for, let's say, a distance of 100 meters, and that object, after the first second, it's moving at a velocity of 20 meters per second. Again, after the next 10 seconds, it's still moving at a velocity of 20 meters per second. In 50 seconds, it's still moving at 20 meters per second. And then when it reaches, say, the last mark, which is that 100-meter mark, it was still moving at 20 meters per second. It means the velocity of the object is not changing for that distance of 500 meters, or that displacement of 100 meters. So the velocity was constant and it was 20 meters per second. Now, that velocity, we say it is constant. Why? Because the object was moving at 20 meters per second for the duration of its motion. It was moving at 20 meters per second for that 100-meter distance, or that 100-meter displacement. As a result, the velocity is constant. Now, an object that is doing that, meaning is the object with which its velocity is not changing for that distance of 100 meters, meaning as it moves with that 20 meters per second, then you can safely say the net force acting on that object is zero. And why is that the case? Because if an object is moving at a constant velocity, it means the object is not accelerating. And if the object is not accelerating, it means your net force is zero. It means all the forces are balanced. Now, it does not mean there are no forces acting on the object. There are always forces acting on that particular object. For example, the force of gravity is one of those, but all the forces acting on the object, they are balanced. It means they give you a net force of zero. And therefore, when the net force is zero, then your object will move at a constant velocity. But When the net force is greater than 0, it means your forces are not balanced, and therefore you will have a net force. In other words, the object will accelerate. And if the object is accelerating, then definitely it is not moving at a constant velocity. It means its velocity is changing. So be aware, when we say an object is moving at a constant velocity, it means the velocity of the object is not changing for the better part of the motion that we are interested in. In summary, what Newton's first law of motion says is, when you are at rest, when a body is at rest, it means the net force on it is 0. When an object is moving, but it is moving at a constant velocity, then the net force on the object is 0. But if the net force on the object is not 0, then the object is going to move, and as it moves, we know that it will accelerate. That is, in a nutshell, what Newton's first law of motion implies. I will read it again for you there. It says, a body will remain in its state of rest or motion at a constant velocity unless a non-zero net force acts on it. Right, so that is Newton's first law of motion. So we engage further. What does this mean? Basically, an object will keep doing what it was doing unless acted on by an unbalanced force. Now, what is this unbalanced force? This unbalanced force is this net force that we are talking about. It is this non-zero net force that we are talking about. Now, when we say an object will keep doing what it was doing, unless this unbalanced force acts on it, meaning if it was stationary, it will remain stationary unless there's a net force acting on it. If it was moving at a constant velocity, it will continue moving at a constant velocity unless if there is a non-zero net force that acts on it, which is your unbalanced force. So if the object was at rest, it will remain at rest. In other words, it will remain stationary. If it was moving at a constant velocity, it will keep moving, but it will keep moving at a constant velocity. And therefore, it takes a net force. It takes a non-zero net force to change the motion of an object. In other words, to accelerate the object. Remember, if the object is moving at a constant velocity, it is still moving. It's just that it is not accelerating. It will only accelerate if that net force is greater than 0. Right. Now, what is meant by a net force? Now, if the forces on an object are equal and opposite in direction, they are said to be equal, and the object experiences a net force of 0, and therefore there is no change in motion. In other words, if it was at rest, it will remain at rest. If it was moving at a constant velocity, it will continue to move at a constant velocity because the net force that is acting on it is a 0. If these forces are not equal and they are acting in opposite direction, then the forces are unbalanced. In other words, the motion of the object is going to change. If it was at rest, it will now start to move, and as it starts to move, its velocity keeps on changing because this object will be accelerating. Why is it accelerating? Because now there is a net force. Why are we saying there is a net force? Because now the forces acting on the object, they are not equal in magnitude, they are not of the same size and they're acting in opposite directions. So it means there will be an unbalanced force, which is our net force, and it will be greater than 0 newtons. And if you check here, let's say we have a physics textbook, and this physics textbook, it is on a surface. Now, you've already sort of done your forces, and you are aware that you can actually draw a diagram that represents the forces acting on an object. So if we look at this physics textbook that is sitting on a table, it's placed on a table. Now, there is a force of gravity that is acting on this textbook, and this force of gravity is acting downwards. Now, because this physics textbook is on a surface, there is also a force that the surface exerts on this textbook. And that force, we call it the normal force. And it is the table that is pushing upwards on the book, because the table exerts a force on the textbook. Now, the reason this textbook is stationary is because this force of gravity has the same magnitude, meaning it has the same size as this force that the table is exerting on the textbook, this upward force that we also call the normal force. In other words, they are equal in magnitude but acting in opposite direction. So this force balances that one, and the net force acting on the object is 0. And because it's 0, it means this object will remain at rest. It will not move because the forces are balanced. Right, so that explains Newton's first law, as well as what we talk about when you talk about net force. So because the object was at rest, it's remaining at rest because the net force that is acting on it, it's a 0. But if this net force was to be greater than 0, then the object would move. Now, let us look at some of the examples in real life where we talk about Newton's first law of motion. Now, let us look at these two teams, and these two teams, they are playing a tug of war. Now, when you look at team A, for example, and you look at team B. Now, team A, if team A was pulling with the force of, and team B is pulling with the force of 700 newtons to the right, it means the two forces that are acting are equal in magnitude, but they are opposite in direction, because the one from team A, it's 700 newtons to the left, and then it is 700 newtons to the right from team B. It means the net force acting on this object is a 0. Now, if the net force acting on this object is 0 newtons, then it tells me they are going to remain stationary. This string will remain stationary. They will remain stationary. Why? Because the net force that is acting on the object is a 0. So the forces are balanced, in other words, and that is why we say these balanced forces results in no change of the motion. Right. Again, if you look at this ball, now this ball is stationary. Why is it stationary? Because the forces that are acting on this object are balanced. So they are giving you a net force of 0. Now, if they are giving you a net force of 0, it means this ball will remain stationary. Now, how can you make this ball to move? to make this ball to move, what you need to do is you need to come and kick the ball. Now, when you kick the ball, you exert a net force at that time on that particular object. And that is why the object will start to accelerate at that particular time when the net force was applied. So you actually have applied the force, and that force will be your net force. For example, when you kick it horizontally, the vertical forces, meaning the normal force as well as the force of gravity, which are acting vertically, upward and downward, they are balanced, and the object is moving on the grass. And let us assume now that the applied force is greater than the frictional force that the ball is experiencing. Then we know that, oh, if this applied force is greater than the net force acting on the object, which is the ball in this case, then this particular ball will accelerate because it has a net force. And hence it says, when a net force acts on an object, then that object will no longer remain at rest, just like the ball was in the initial stage before it was kicked. Now, Newton's first law of motion is also called the law of inertia, right? And we need to then understand what are we talking about when we talk about inertia. Remember now that inertia is the property of a body to resist change in its state of motion or rest. The property of a body to resist change in its state of motion or rest. In other words, if an object is actually stationary, it actually wants to remain stationary. If an object was moving, the object wants to keep on moving. If the object was moving forward, it wants to continue to move forward. If the object was moving backwards, it wants to continue to move backwards. And in that case, you know, when you have, for example, let's say you take, you are in a car, right? And you are a passenger and someone is driving, and the person is driving, say, at a velocity of 120 kilometers per hour. Now, if, say, a dog all of a sudden runs into the road and the driver sees it instantly when he is closer to that particular dog, what normally the driver would do is he would apply brakes all of a sudden, and it might be a very strong brake at the time. So what you normally experience is that you will go forward and then you will come back. And the reason is because your body at that time, before the brakes were applied by the driver, was moving forward. And because it was moving forward, when someone like the driver suddenly applies the brakes, it means now your body did not actually want to stop. It wanted to continue to move forward, and hence you go forward and then you return back to your original position. And if the car stops, you will also stop. It is because the body resists to change its state of motion, its state of going forward. And hence, you went forward and came back. Now, you know, with objects, the bigger the mass of that particular object, the more inertia that object will have. Let me give you an example. Let us say you have a box, right? And you are trying to push a box that is on the floor. If that box has a small mass, it won't be that difficult for you to actually move that particular box. So yes, the box will still resist to move. It will still resist to change its state of rest. But because the mass is smaller, you might find that it becomes a little bit easier for you to change its state of motion or rest. But if the object was bigger, and you try to apply the same force that you applied on a smaller box, you will see that it will be very difficult for that particular object to move. Why? Because the object has a bigger mass. So the more mass an object has, the more inertia that particular object it will have. The more that particular object will resist to change its state of motion or rest. And hence, there they tell us, the more mass an object has, the more inertia it has, and the harder it is to change its state of motion. Right. Now, this picture here, it's in the Department of Basic Education Exemplar 2018, Technical Sciences, and it emphasizes the importance of safety belts because we use Newton's first law of motion to basically apply this concept of how our safety belts help us and why we need to put our safety belts at all material times. Now, the question here is, what would happen if the driver was not wearing a safety belt? Now, according to Newton's first law of motion, the driver will continue to move forward and may collide with the car steering, the windscreen, which will exert a force on him that may be fatal. Now, what you should actually be seeing on this particular picture is that there is a driver in there and the driver was moving forward and there we have a wall and this driver crashes into the wall and hence we ask ourselves, what would then happen if this driver was not wearing a safety belt? And we explain there, if this driver was not wearing a safety belt, remember now, when you start to apply when you start to crash into this particular wall, now you are involved in an accident. So this is actually a collision. Now the car is most likely to stop or it will hit the wall and it will move backwards. So those are likely scenarios. Sometimes it can crash into the wall and actually continue to move forward. Now, let us say on impact, what is essentially going to happen? Now, that particular impact, this wall will exert a backward force on the driver, right? And if the driver is not wearing a safety belt, when he immediately crashes into this particular wall, his body is going to move forward, right? And if he's not wearing a safety belt, depending on the size of the force that he's experiencing, he can actually move into the windscreen. And when the windscreen applies a force on him, then depending on the magnitude of the force of the windscreen, then that particular force may result in severe injuries to the head of the driver or to any parts of the body that are going to collide with that particular windscreen. And in other cases, if the force is really, really large, then the driver will then will experience an injury that is quite fatal. So if we wear safety belts, it means as we move forward, right, because of the body was continuing to move forward, then the safety belt will then apply a force that opposes the forward motion, and then it will bring the driver back to the original position before he or she even hits the windscreen. And hence, it is important for you to be wearing your seat belt, which is your safety belt, at all material times. And here, I also indicate the worst case scenario, and we say the driver may exit through the windscreen and collide with the road, and that is definitely fatal. Now, that is all in all what Newton's first law of motion is about, and it also teaches us, of practical applications where we definitely need to wear our safety belts so that we do not get injured when we get into an accident, for example. Now, we are going to look at Newton's second law of motion. And Newton's second law of motion is very important because there are a lot of calculations that you must be able to do. And tomorrow, as we look into Newton's third law of motion, we will be reverting back to Newton's second law of motion, and we will be doing quite a number of questions on this particular topic. Now, Newton's second law of motion states that when a net force is applied to an object of mass m, it accelerates the object in the direction of the net force. Acceleration is directly proportional to the net force and inversely proportional to the mass of the object. Now, this law is as it is from your examination guideline. Now, some of the textbooks that you learners are using, you will find that it says when a net force is applied to an object of mass m, it accelerates the object in the direction of the net force, and it ends there. And that will give you a problem because the full law wants you to go further to give us the relationship between acceleration and net force, as well as the relationship between acceleration and mass. And that is why I am warning against using, stating laws as they are in the textbook. Please state them as they are in your examination guidelines. So, again, when we state it, my dear learners, remember that part there where it says when a net force is applied to an object, if you omit the word net, then this entire law that you have stated becomes incorrect, because it is not just accelerate. The object accelerates because of the net force, because of that single force that has the same effect as all the forces acting together on an object. So it is the net force that is responsible for the acceleration of the object, and not just the force. And hence, we need to emphasize the word net there. It must be there, otherwise you will not get a mark. So basically, to explain this, if the net force acts on an object, the object will accelerate. If the object does not experience a net force, then the object will not accelerate altogether. And if it is accelerating, it will definitely accelerate in the direction of the net force. Now, acceleration is directly proportional to the net force. Now, this is the relationship between acceleration and net force. It means if the acceleration increases, if the net force increases, then the acceleration is also going to increase. That's essentially what it means. And then to emphasize more on that, for example, let us say the mass of an object is 2 kilograms and the acceleration is 1 meter per second squared. If you double the net force, meaning you take the net force to 4, then the acceleration will also double and it will be 2 meters per second. The acceleration is also going to double, but that is only if you do not change the mass. So the mass has to be constant. So acceleration is directly proportional to the net force. You increase the net force, the acceleration increases. For example, you double the net force, then the acceleration is going to double. Only if the mass is kept constant. And it is inversely proportional to the mass of the object. Now, what is inversely proportional to the mass of the object is acceleration. So, if the mass of the object increases, the acceleration will decrease. If the mass of the object increases, then the acceleration will decrease. Or if the mass of the object decreases, then the acceleration will increase. But that is only true if the net force is kept constant. Right, and we know when you talk about acceleration, we are talking about the rate of change of velocity, how fast our velocity is changing. Now, the formula that we use to study the relationship between net force, mass, and acceleration is here. It's given as Fnet is equal to ma. And you need to write that net altogether because it is the net force that is responsible for the acceleration of the object. And my dear learners, I know some of you go through quite a number of textbooks and you might find that it's written F is equal to ma. Please, you have to write it as you get it from the formula sheet which comes with your question paper, and you will find it as Fnet is equal to ma. Now, what does Fnet equal to ma mean? I've already said this to you. Net force is directly proportional to mass and acceleration. Well, in this case, it is the net force that is directly proportional to the mass. At the same time, it is directly proportional to the acceleration. In other words, if you increase the mass of the object, and if you increase the mass of the object, then the net force is also going to increase. If you increase the acceleration of the object, the net force is going to increase. If you increase both the mass and the acceleration of the object, the net force is also going to increase altogether. So according to this equation, Fnet is equal to ma. If a ball has a certain mass and it has a certain acceleration, then this ball is definitely going to have a net force. It means if the value there it's 2, for example, and the acceleration there it's 2, it means the net force will be 2 multiplied by 2, and that will give you 4 meters per second squared. Now, what would happen if you take that same ball and you double the mass, but you keep the acceleration constant? In other words, this, remember now in our previous example, the mass was 2, the acceleration was also 2. So this was 2 kilograms, this was 2 meters per second squared. If we double the mass, meaning we make the mass 4 kilograms, and we keep the acceleration constant, it means now the net force being calculated, it will give us 4 multiplied by 2, and that will give us 8 newtons. It means now this ball will have twice the force as the old ball, because the old ball had a net force of 4 newtons because the mass was 2 and the acceleration was also 2. But now the mass in the new ball is 4 kilograms, but the acceleration is still 2 meters per second squared, so we get 8. In other words, we go from a net force of 4 to a net force of 8, and therefore it means our net force has doubled. And that is why we say this net force is directly proportional to the mass. It means if you double the mass, the net force will also double, but that is if the acceleration is constant. And we can, do the same thing again, and now we make the acceleration to be 2 times what it was before. But we keep the mass constant, meaning the acceleration is now 4, and the mass, now we keep it constant at 2 kilograms. The net force will still be 8 newtons, so it means this net force has doubled. Why did it double? Because the acceleration was doubled, but the mass was kept constant, and that is what we mean by direct proportionality there of net force with mass and acceleration. So to elaborate further, if you double the mass, you double the force. If you double the acceleration, you double the force. But what if you double both the mass as well as the acceleration, right? If you double the mass and you double the acceleration, it will now be 4 times larger than what it was. Are we clear, my learners? So if we, for example, take the mass and we still substitute it as m, and we take a, we still substitute it as a. If we double this, make it, meaning we make it 2m, and we double the acceleration, we make it 2a, we can see that the force will be 4f. It will be 4 times bigger. So to look at this equation further, it basically tells us that the net force of an object is definitely determined by its mass as well as its acceleration. So it's not because of the mass only, and it's not only because of the acceleration, it's because of both the mass as well as the acceleration. For example, if you look at a bullet, we know a bullet is quite deadly. Now, someone would basically ask themselves, why such an object that is so small, yet it can be so fatal? If, say, the mass is because it exert on the other object, for example, the human being. If the mass of the bullet, for example, it's 0.2 kilograms, and its acceleration, we definitely know that it's going to be high. And the reason we know it's going to be high, it is because its velocity changes by very quickly. You know, when you look at bullets, they can go at a velocity of 200 meters per second. And if you look at 200 meters per second, meaning when it started, it wasn't moving when it was inside the gun. And now when a shot has been made, you find that the velocity changes from 0 to 200 meters per second in, let's say, 3 seconds. Then its acceleration is going to be very high. And when the acceleration becomes high, then the net force is also going to be high. And hence we say something very small that is changing speed, or rather velocity, very quickly, will have an acceleration that is high. And a good example of that is a bullet. And that will definitely give you a very large net force altogether. So it's something that is quite small, but you find that it is having a larger acceleration, and therefore the net force experience is going to be large. And in our next lesson, we are going to learn the following regarding Newton's second law of motion. We will learn how to draw free body diagrams. We will learn how to correctly determine the direction of forces. We will learn how to calculate a net force. will look at types of forces like frictional force, and will differentiate between static as well as kinetic friction, and will also engage further as to when an object experiences static friction and when does it experience kinetic friction, and will learn how to calculate acceleration using the relevant formula. Now, to prepare for this particular topic, my dear learners, remember at the end of the year, it is going to be your paper 1, and you will get your multiple choice questions being about 6 marks and your long questions being about 26 marks. In other words, this topic alone, from Newton's first law of motion to Newton's third law of motion, is going to give you plus minus 32 marks out of 150. And that is 21% of the question paper, and you can really do well. Now, I wanted us to really just look at a simple example there, just to assess each other. Now, right, sorry about that. Right, my dear learners, I just had a small assessment here that we can do in just a minute or so. So, say you are given the net force acting on an object, and you are given the mass of an object in kilograms. Remember there, it's a small letter M. I don't know, just a small change that happened there. I think it was just my settings, as well as acceleration. Remember, it is a small letter and it is measured in meters per second squared. So if I were asked to calculate the net force that is acting on this object, I would then say, I need to use Newton's second law of motion, and it says there, the equation Fnet is equal to ma, right? You remember that. So where I see Fnet, I would substitute 20, and where I see mass, which is m, I would substitute 2. And then to calculate my acceleration, I will see that my acceleration will give me a value of 10, because it will be 20 divided by 2. Then, if my acceleration is, if my net force is 40, then my mass is given as 2 again, meaning it's not being changed. If I go now and I calculate the acceleration, it means I will take the value of the net force, which is 40, I will divide by the mass, and I will see that I am getting a value of 20 meters per second squared. Now, what are we learning from this relationship, my dear learners, is that we kept the mass the same. We didn't change the mass of the object, but we have doubled the net force from there, from 20 to 40. And now we can see that the acceleration has also doubled. So this explains that relationship where we say acceleration is directly proportional to net force, because from this to this, right, from scenario A to scenario B, we can see that we doubled the net force and the acceleration doubled. Why? Because we also kept the mass constant. So that relationship there where we say acceleration is directly proportional to net force is only true if our mass is kept constant. Now, I want you to see this again. There I have a net force of 20. I still have a net force of 20, but the mass was 2 there, but now I'm making the mass 4, meaning I'm doubling the mass. If you look at scenario 1 and scenario 3, the net force acting on the object is the same, but the mass in scenario 3 is 2 times the mass in scenario 1. Now, if I go and I calculate my acceleration will be Fnet is equal to MA. Where I see Fnet, I will put 20. Where I see the mass, I will put 4. And if I work out my acceleration, it will be 20 divided by 4, and that will give me 5 meters per second squared. So now we can see that if the relationship there between mass and acceleration is that if I increase the mass, then the acceleration is going to decrease, because there I had a smaller mass but a bigger acceleration. But when I have a bigger mass, then my acceleration becomes smaller. Or rather, let me repeat that. If I have a smaller mass, my acceleration is 10, meaning it's larger, compared to when I have a smaller mass, rather a bigger mass of 4, and my acceleration becomes smaller, which is 5. So the smaller the mass, the larger the value of the acceleration. The bigger the mass, the smaller the value of the acceleration, provided the net force is not being changed, provided the net force remains constant. Are we clear, my dear learners? Right. So thank you very much. If you have any questions, feel free to send them to send them to STEM Digital's school at africateengeeks.co.za. And I just want to leave you with this note as well, that you must remember that once you stop learning, you start dying. So you need to work very hard. So in a nutshell, my dear learners, tomorrow we will be engaging further, meaning we will be looking into questions that you